Thanks for coming. I want to talk about consistency, about transactions. I want to actually jump into an example. We have 30 minutes. 30 minutes is not a lot of time. So we'll make it rather quick. I'm around for a question afterwards. So if some of the things are too quick now, don't hesitate to ask me later on. I want to use an example which is kind of the classical example for the problem. So you find a lot of resources about exactly that example in the internet. So it's at least worth to look at that today. Like in the real world, you might do different things, but I hope you can relate to that. So let's assume you have like 3 functions. Let's say lambdas at AWS, for example. You want to book a rental car, you want to book a hotel, and you want to book a flight, right? So this is basically the functionalities provided by certain lambdas. But what you want to actually do is basically providing functionality to book a trip. As soon as you have something like that, you have what I call here collaborating functions. So somehow they have to collaborate in order to provide the whole trip booking. There are certain ways of doing that. I'm not going over all of them. The thing most people tend to do in that situation is kind of doing kind of a coordination function or kind of an orchestrator. Like you could say, hey, I have that trip function, and this one is calling, first it's calling the car function, and then it's calling the hotel booking function, for example. Right? There are a couple of upsides and downsides of that. I'm not going into too much details of that. There's an own talk. I have slides online, and there are a couple of other talks. So if you are really interested in like what are the different ways, what I can do there, I'm leaving that up for today. But let's assume you do this, right? There's one thing you have to solve, and that's actually a quite hard one. So let's assume there's somewhere in that process there's a problem, like you can't book the hotel. You probably don't want to have the rental car if you don't go on the trip at all. That's a thing we know from like traditional architectures or traditional programming under that term ACID. Who does know what ACID stands for? I'm not asking anybody, so you can be brave. Okay. I had to look it up when I once prepared the talk at the first time, to be honest. I know it from my university time, but a lot of things are gone. It's for atomic, consistent, isolated, and durable. So if you do like transactions, they have all these properties. And I mean, durable, that's kind of like a database thing. If you store something, it's still there. That makes a lot of sense. It's isolated. That means if you have different threads, like trying to access it at the same time, they are isolated. So only if you committed something, like really in the ACID manner, after the commit, somebody else can see it, otherwise not. I'm making an example of that in a minute. And it's consistent. That's sometimes a bit weird here, but consistency normally relates in ACID for, I have, for example, database properties like non-null constraints, foreign key constraints. So it's consistent in itself. And atomic, that's what I'm talking about. You want to do like 3 steps in an all or nothing semantics. Either everything happened or nothing, right? And that's ACID was quite easy to do when we did programming in like one language. But now we start to do these like distributed systems, and it gets harder and harder. So if we look at that example, like we have these 2 functions we want to call, and the second function fails. There's no way of really like doing a rollback of that transaction because you don't have a transaction actually. If you look at that code here, whatever programming language you use, you don't have a transaction manager where you can simply say, hey, roll it back for me, please. There was, and I'm asking that, I'm actually quite curious about this community, like the AWS community. Who has heard of two-phase commit? I'm asking that all the time. A lot of people, like 10 people probably, not a lot, but who has used that in production? 1, 2, 3, that's a lot. Who is happy with that? Okay, nobody. Okay. For the whole rest, there was an idea, like I think 10 years back was kind of the peak when people said, hey, we want to do two-phase commit, which has kind of a transaction coordinator, coordinating different resources in order to do like a really ACID transaction in a distributed environment, right? I don't want to explain all the details. It's quite complicated. And the interesting part is it doesn't really work. If you want to read about that like in detail, there's an awesome paper. I'm a big Pat Helland fan. Pat Helland worked at that time at Amazon. He's currently at Salesforce. He did a couple of other big companies in between. And he wrote a paper, Life Beyond Distributed Transactions. And that's a pretty good paper. It's really fun to read. And he explains very well why this concept of distributed transactions simply doesn't work in bigger distributed systems. It limits scalability and it's too complex to really work. So his own quote is, grown-ups don't use distributed transactions. So I think that's the important thing to remember. Assume we don't have like asset transactions in distributed systems, like for example, calling different lambdas. There is no transaction manager. That's something you should take as like the basis, as given. That's actually not so new. So there, if you search for it, you can find, for example, that slide from Eric Brewer. He's one of the Google guys. And he did that on a keynote in the year 2000. So it's quite old, right? But he already said, hey, we have to forfeit C and C and I is from the asset for availability, graceful degradation, and performance. He basically says, if we want to build a, let's say, decent distributed system which behaves performant in a way, and we want to scale that, this is fundamental. We can't build that with the whole asset guarantees. It's just not possible. We have to get into a different world. He named it BASE, never took off that acronym. Basically available soft state, eventual consistency, but this is where the term originally was coined, like eventual consistency. So that's Eric Brewer. It's quite old. But now we start to really see people at least hitting it or probably starting to understand that. And it basically means, it's relatively simple, but it's important to have that in mind. It basically means when we do like two function invocations here, they might have local asset. They might have local transactions, right? But we don't have a transaction spanning both of them. It basically means in the meantime, like we booked the rental car, but we couldn't yet, or we didn't yet book the hotel, we're inconsistent. It's not isolated. That's a tricky part. It doesn't violate the consistency. It violates the isolation. Because now if somebody else from the outside looks into the system, he sees a rental car booked, but the trip is not yet successful. Okay, that violates the isolation. It's not a bad thing. It's not a problem. I will talk about how to deal with that in a minute, but it's important to really to get that into your head. It's kind of a different way of building architectures, of building applications, which was quite different 10 years ago. Pat Helland once named that Asset 2.0. I like the term much more. He's better in marketing. And when he wrote that paper, 2.0 was the thing, right? So it's probably a bit different today. So he said, if we want to build distributed, scalable systems, we have to make systems that are associative, commutative. That's a bit about ordering, right? I have the math terms here. It basically, you can imagine it like in a way, if you have messages, they don't have to arrive in order for the system to work. That's more or less what it is. If you build your system in such a way, it's much more robust, it's much more scalable. You have to make them idempotent. I will talk about that in a minute. That's an important characteristic. I think from my perspective, one of the most important things, make things idempotent. It means that you can basically call them twice without the world exploding for some reason, right? It's important. And distributed. And the distribution part, that's the one where you don't have any choice. I mean, you can still build a big monolith in the whatever mainframe down the cellar, but that's normally not what we do in order to make it scalable. We build distributed systems. That's the metaphor I always use for distributed systems. I learned that actually from Jonas Bonnet. He is the Lightband guy behind cker and certain frameworks. And there's like the small hut, for example, over there. That's your one function. That's your application, your service, probably even one Docker container or whatever. It's, you know what's going on there. It's relatively cozy to be in there. But when you open the door, there's that rough ocean, and that's the network. And the network does weird things. And it's not binary. It's not like it's there or not. It's partly there. It probably delivers part of the messages, out of order and whatever. You might, or you should know actually, the fallacies of distributed computing from Peter Deutsch. You can look it up on Wikipedia. And the top, or the first one, it's not really like priority, but the first one is the network is reliable. It's of course not reliable. Networks are by definition not reliable, and it's a hard thing to deal with. And to make two easy examples here, which are important to keep in mind, like if we have that function here and calling other functions, we do that via network connection. The network connection might fail, right? So it might simply not be available. We get a whatever error when we try to call the function. And that will always happen, even if you scale the function, even if you whatever, that can always happen. So as soon as you have that, what you typically do, it's a very easy pattern actually, but you do retrying. It's even built in a lot of frameworks. You can easily retry. Hey, it didn't work, I try it again. Right? Very simple and very, makes a lot of sense to do it like that. But the important thing to recognize here is that you have to build your architecture in a way that you're able to do the retry. So you have to build that function, for example, in a way that it's idempotent, that it can call it again, right? In this case, it's very often about like parameters. Like, for example, I could have a trip ID, which I generate already in the first part of the picture in that function, and then just pass it on to the other functions. And they can recognize, hey, I already got that call, so I don't execute it again. I probably even already know the result and give it back or whatever. It's sometimes very easy to do it on that side. A lot of people forget about it. It's pretty hard if that function doesn't offer that to fix that on the calling side. So idempotency, from my perspective, is one of the really most important things in these kind of architectures. That's kind of my favorite slide. That's a zucchini. I had, I must be 9 years back, I had a time where I ate only vegan food. It was kind of a try. I was quite happy with it, but actually there are two hard showstoppers for eating vegan. The first is traveling, the second is kids. So that I really stopped. But there's an awesome dish. I love that dish. It's you make noodles out of the zucchini. There's a special slicer. You slice the zucchini, you get the noodles out of the zucchini, you add some sauce. Very tasty. Totally can recommend that. In the book, it was vegan for fit or something like that. They write you can eat that in the evening. It's allowed in the evening because it's very healthy. And that was an interesting part, you can eat as much as you want from that. So I search for metaphors, actually. That's what I do a lot. And with that dish, if you ate your plate of zucchinis, you can just eat another one. Or another one, or another one. Eating zucchinis is quite idempotent. Pasta is not. Yeah, I know it's not my best metaphor. I totally agree. But the important thing is that it sticks. For me, that's really important. I see that problem in so many projects that you simply don't have idempotent functions, idempotent services, idempotent APIs. And that causes so much trouble. So if you provide something, make it idempotent, makes the world a little bit better. But make a second, make a second example in distributed systems. So even, let's assume you have an idempotent function and you call it, and you get a network error. The problem with the network error is you have no idea which of the three cases just happened. All of them could be, the first is the network was broken when you were still on the way to the function, let's say. It could be that you called the function correctly, the function started working, and then it exploded for whatever reason. Could be a bug, could be whatever, just the VM crashes, whatever, and it doesn't return anything. Then you have no idea, did it commit its transaction or not? You don't know. Or did it do anything correctly, but the response got lost? And if you're not in calling it via whatever REST or API gateway, use a Kinesis message or SQS or whatever, you send out a message, never get back a response. You have no idea what happened. And the thing is, you have to think about that, not in all of the use cases, but in some of them you should. In this case, if you do correctly and you say, hey, I want to book the hotel and it didn't work, you get a network error, you have to think about cleaning it up, for example. You have to think about, hey, I couldn't book the hotel for a network error. Probably I retried for a couple of times, but then I give up. And when I give up, I have to think about, but I probably booked that hotel. It could be. You don't know. And especially if you're caring about payments, it's probably nothing you want to ignore. right? In some use cases, you can ignore it, fine. If you do that consciously, I'm happy with that. But in some use cases, you can't, okay? So you can see that this gets more and more complicated. And one thing, I'm quite biased on that. I'll give you the hint in a minute. But what I see a lot of customers currently and users moving towards is that because of that complexity, move that into some like separate component. And this is, I would call it a workflow engine. If you're quite deep in AWS, could be something like step functions. If you know step functions, that's the thing in the AWS universe. I would call it like generically, it's a workflow engine. And it basically can take care of this workflow. And yeah, that's what I mean. Just to make my opinionation kind of transparent, I'm co-founder of Camunda. We're an open source workflow, basically open source tool vendor for workflow engine. But I'm working with workflow for roughly 15 years now, contributed to different open source workflow engines, knowing a lot of them quite by heart. So that's my background. That's why I'm also looking to like a lot of problems through the lens of workflow engines, okay? That's probably good to know for you, then you know what I'm talking about. And I also, quite a while back, I wrote a book about something called BPMN. And BPMN is a language. BPMN is a workflow expression language. It's an ISO standard that makes it quite interesting, and it's very powerful. Coming back to that in a second. And you can express these workflows, for example, in BPMN. I have the same example in step functions later on as well. You can also do that. So the language, it does matter, but for the moment, all of that would work. And then you could say, okay, I still do the same thing. I express that workflow, like do these three things in a row. And then you normally have built-in functionality, for example, for retrying, for things what I call stateful retrying. That's very interesting sometimes. So like retrying immediately might not help because you're currently in a downtime, a redeployment cycle, a severe network outage or whatever. Then you might want to wait for minutes or probably even hours to do the retrying. And that's what a workflow engine can do because it keeps things persistent. It can wait for whatever to happen. And that's pretty interesting here as well. But we haven't yet solved the asset, right? So this is probably gives you kind of the retrying, gives you probably a couple of things to think about, but we haven't yet solved the asset. And if we look into that, that's actually quite interesting. That's a book which came out last year. I totally recommend that. Probably a couple of you know. From Martin Kleppmann. He wrote about basically also highly scalable systems and quite a lot of gold in there. And he gave a talk at Strange Loop 2015. It's quite a while back, but he has more recent talks, but I like this because of the slides, actually. You can look it up on YouTube. And there he had one thing where he talked about, hey, if we don't have cross-service transactions, that's what I had in the very beginning, if we don't have XA or two-phase commit transactions, then we basically have two possibilities how to deal with that. I start with the second. It's apologies. It sounds weird, but it's actually a very natural thing for a lot of problems. You don't really stop things from going problematic, but you can detect them afterwards. So you can probably you run a whatever reconciliation job once a month or these kind of things, and then you see, hey, there were problems. And then you apologize for that with the whatever internal department, with the customer, whatever. It's kind of the thing you order at Amazon and you see you get it delivered within 24 hours because it's on stock. And then they see, it wasn't on stock really. So they send you whatever. Oh, we're sorry, there's a delay. Here's a whatever, €5 voucher or something. That's apologies. But the other one, that's the one I want to look into today, that's the interesting one, which is called Compensating Transactions. And he describes it as abort or rollback at the application level. So we don't have a transaction manager, which just rolls back, but we want to do it on the application level as kind of a business logic. And it works like that. If we go back to that example, we book the hotel, the rental, the flight. And let's say the flight can't be booked for whatever reason. Then what we do, we can't just simply roll back, but we trigger so-called compensating functions, like undos. Like in this case, it's canceling the rental car and canceling the hotel. Right. It's another call. It's not that it's not really like undone. It's not really rolled back. You might see that. You might even be charged money for that, right? But that's the only way how you can do that. And this all basically ends up with, now I'm eventually consistent. I'm not consistent in the middle, but at the very end, I will be. It's very often known as the saga pattern. So if you want to Google for that, that's a term which is currently used a lot, saga pattern. And then you also find that example actually used quite a lot. To implement that pattern, and that's actually interesting. I love that topic. I'm talking about that topic a lot recently. There are two approaches of implementing that. And that's not only for the saga patterns. It's basically also how different, like for example, microservices can interact to do something. And one is choreography, the other is orchestration. I want to quickly introduce both of them. You might get an impression what I favor in some cases. One thing could be a choreography, and that works a bit like you have a trip component, might be a function, might be a microservice, whatever that is for the moment, and this gets ordered to book a trip. And then what it could do is like, the choreography is kind of an event-driven thing where you say, hey, there was a trip requested. You basically send it out, probably on an event bus. That's the idea of an event-driven choreography. But you have no idea who is really picking that up. And then the hotel service says, oh yeah, trip requested, I have to book a hotel. And it's another event. And the rental car service knows, oh, if there was a hotel booked, I have to book a car, and so on and so forth. So it's kind of an event chain. If something goes wrong, and that's the happy case, so everything worked. Yeah, we booked everything, trip is booked, we're all good. If something goes wrong in the flight, it basically works like the reverse order. Hey, flight couldn't be booked. So the car service has to listen for that and said, oh, then I have to do the undo and emit another event. And the hotel service said, oh, if the car was canceled, I have to cancel the hotel, and so on and so forth. Right? You get the idea. Right? You might do it like slightly different, but that's more or less the idea. Right. I'm personally not a big fan of that picture. There are advantages of choreographies. It's very often the idea of it's more decoupled because you just react on events. And that's true for some use cases. But in this example, you see very easily that you have that flow, that workflow of events, but you can't see that anywhere. It's pretty hidden in the different components. You have to, go to your logs or to your tracing tool in order to understand what just happened, right? And I was personally, because I'm discussing that really on a very regular basis, I was very happy when that blog post came up from Martin Fowler. It was already in 2017. And he said the danger is very easy to make nicely decoupled systems with event notification without realizing that you're losing sight of a larger scale flow and thus set yourself up for trouble in future years. Which is kind of understandable. I mean, if you don't understand the flow anymore, how do you want to change it? How do you want to implement anything in there anymore, right? At a recent QCon in New York, Phil Calando from Meetup, he named it the pinball architecture, which I think really nails it quite well. And you can make examples. If you just want to change the sequence of things, hey, we want to book the rental car first. We have a good contract because we can now cancel rental cars for free. If you just want to make that change, you have to touch each and every service or function or whatever it is, right? And then you have to redeploy it. And you probably even have to think about, if you do it event-driven, you have messages flowing around your system. You have to think about every situation they might be in, about versioning, and so on and so forth. So it's not simple, right? For me, so that's the point where you can guess my personal opinion on that. But this is normally the slide how a lot of people sell the idea of choreography. It's kind of that dance, and the dancers are kind of the different services. Everybody knows the rules, and they're professionals. So you can add whatever dancer you want, and they're just will be beautiful, right? You don't have to explain them, you don't have to choreograph them. But it's not what I see in the real-time projects out there. It's kind of very chaotic sometimes. It's very hard to manage, actually. Right? So what's the difference, or the different approach? It's like, hey, I want to do orchestration. So the trip could do that. The trip could orchestrate the others and say, hey, the first thing I do is book the hotel. Hey, I'm done. Book the car. Hey, I'm done. Book the flight. And now you have that one point where you can put in all the logic, and when you can change the sequence. Right? And then you could say, hey, this orchestrator, this trip, that's one thing where you can change everything. And there you could also implement that Saga logic. And that's a Saga, for example, in BPMN, where you can say, hey, I reserved the car, I booked the hotel, and so on and so forth. But whenever I have a problem, this is the compensating action. It's already defined, so you can trigger a compensation. I have to roll back, then you can directly do that. Okay? Cool. Yeah, I wanted to do very quickly. I wanted to do something live very quickly, which is quite challenging in 30 minutes. So I'm basically showing you something, giving you the hint where it's on GitHub, because then you can either play around with it yourself or you can approach me later on. And I'm happy to walk you through all of it. But for the moment, I'm just giving you a very quick idea of what I'm doing. It's all on GitHub. There's a YouTube tutorial. I basically recorded that when I did a test drive for this one, so I'm sure it works. It's 15 minutes. We don't do the 15 minutes here. You get the 10 seconds thingy or whatever. And what I do is I basically implemented that thing. I have functions for each and everything. That shouldn't be too surprising here. So I have Lambda functions for the different functionalities. They basically don't do anything here. I use serverless framework to deploy them. That's quite boring, I think. And then what I did is I defined my BPMN flow. In this case, I use CB. Did I introduce that? I think here. CB is an open source workflow engine that can execute BPMN. It's kind of cloud native in the way it's built, so it's really scalable. And there's a cloud service, a managed service available. Not on AWS directly, but in this case from us. But I have the step function thing as a comparison in a minute. And with that one, the architecture I'm doing is I'm basically having my functions. That's the one you just saw. Then I use that Camona Cloud thing in the back. And then I have one function to call the trip booking, and that also defines that workflow model. And then it basically uses, in this case, it's gRPC to talk to the workflow engine, and the workflow engine talks API gateway REST back. It's not the only possible architecture. There are a couple of them. In the blog post referred in the GitHub README, I discussed different approaches. But for now, that's the thing I want to do. So that's basically here my cluster for the workflow engine. You get a couple of credentials. I basically pass on a couple of my AWS credentials in order that they can talk to each other. And then I can, for example, look into what's currently going on. And what I can see, and that's basically more or less all I can do here, is a workflow. It looks a bit different than on the slide. If you want to know why, I explain you that in a minute, like after the talk, if you like. So it's deployed there. And what I can do then, let me quickly show you one thing. So my trip booking function, if I look at that, what you can see is that this one now basically just talks to, in this case, it's called CB, and creates a new workflow. That's everything it does. And I can trigger that. Let's quickly do that. Trigger that using curl. So a new trip booking got started, and what you can see is like we currently had two. So one in the morning when I set up the cluster, one like early on when I tested the Wi-Fi. Now we have three. And if you look at them, just to give you an idea what workflow execution means, is you can see all the steps it walked through, like what was exactly the path and so on and so forth. And what I quickly can do, and then I have to jump back to the slide, let's simulate a flight failure. And that's the payload I pass through my workflow, just for simulation purposes. If I do that and curl it again, and if we go back, if we refresh here, we should have our fourth workflow. Where's the fourth workflow? There it is. It went another way, and then it can look like what's the exact path again, like, and then it canceled the flight and so on and so forth. That's one part, and let me do one thing very quickly, and then I'm almost done. Yeah, I have to look at the time. Let's quickly delete a function, because I like to whatever, which one? Like delete the one that books I even forgot. We will see that in a second, which one I just deleted. If I curl it now, what you can see is, refresh it. Probably that has a small delay here. What you can see is that it ends up with a so-called incident, with an error. And that's one of the things which I find important always to differentiate. That's the thing where you can do retrying, a technical failure. And the other ones are business failures, then I do like the compensating part. And you can handle kind of both with that technology. If you ask yourself like, oh, graphical models, I want to program, that's another discussion I have very often. I want to point you to one blog post from Clemens Fasters from Microsoft. He wrote about sagas quite a while back, and he basically explained, same example, explained how he did it like all over the place, but he started with the picture. So I think it's really important to have these kind of pictures, to really understand what's going on. It's what's very often referred to as living documentation. So it's executed code, but you can understand it, right? From different perspectives, like operations, like really make sense of if it's a good workflow, where do we have bottlenecks, and so on and so forth. And that's one of the concerns, for example, I have with step functions. So the visibility is not really great, the operations is not really great, and the power of the language is not really great as well. But that's an example, same thing, in this case from Jan, for step functions. So that's probably, if you can't go for anything else, that's better than nothing. That's my take on that. But then probably think about more complicated scenarios. That gets quite hard with this. So quick recap. Function coordination is an important topic. It might include orchestration and workflow. Carefully decide about choreography versus orchestration. Both have merits, so normally you have to balance them. Grown-ups don't use distributed transactions, so you're in a world of eventual consistency. Their idempotency is super important. Always think about the zucchini. And no saga as a strategy. I think that's very important. That's all I have. Thank you.
Great. Thank you, Bernd. OK, so we've got one lightning talk before lunch. Quick question for Bernd before we have the next talk. Any questions? No. Wonderful. Another round of applause then. Thank you.